Good morning, everyone. So today we are going to revise the topic of properties of fluids, and we'll start with surface tension. If we compare liquid, gas, and solid, there are some key differences. In case of liquid molecules, they have significant intermolecular force of attraction, and which results in, and we know in case of just we had done a gravitation topic also. In case of gravity, two masses also have force of attraction. If there's a significant force of attraction, it leads to negative potential energy. So here also there's so many molecules, though the force is small, but there's so many of them, so it results in negative potential energy, and this is because of significant intermolecular force of attraction. And what happens, so if in case of liquid molecules, see, like water also. Water could exist in liquid form, it can exist in solid form, it can also exist in gas form. So what is the difference in water which is in liquid form and in the gas form? In liquid form, the molecules are at close distance from each other. So there's a negative potential energy. So to convert water into water vapor, you need to separate them. And when you need to separate them, you need to supply energy equivalent to potential energy, something like escape velocity. So here they need, so energy needed to separate molecules to large distance. So energy what is required to vaporize or evaporate. So that's why, and when we take any part of liquid here, so any molecule, if you focus on one particular molecule, it will have several molecules surrounding it in all directions. But this is what happens in case of molecule which is situated in the interior part of a liquid. What happens to liquid molecules which are near the surface? What we talk about surface means there's one side is liquid, other side is air. So it's a boundary between air and liquid. In this case, if I compare these molecules, which are all molecules which are present here, so compared to other molecules which are present in the interior region, it has only half as many molecules around it. And hence its potential energy also will be because of half of them. And accordingly, so if a molecule here in some unit has potential energy of minus 10 units here, this will have only half of it. It will only half the potential energy a molecule would have had in case of interior region. So which of the two have a higher potential energy? So compared to this is a lesser negative value. This has higher energy compared to a molecule here. So they possess extra amount of energy. So all molecules which are near the surface, they have extra energy compared to molecules inside. And how much is that extra energy? Extra energy is equal to half the energy needed to vaporize it or to separate it. So in a way, it is linked to the heat of vaporization. So there's extra energy associated. And that's why we call it, and larger the surface is, and the energy will be proportional to surface area. So that's called, it results in what we call as surface energy. And there's energy also, whenever there's potential energy, as it moves from here to some other region, if the potential energy changes, it means there has to be some force also present. So there's an associated surface tension force as well. So near the surface area, they possess extra potential energy and compared to interior region. So if potential energy is more here, potential energy increases opposite to direction of force. So there's some net force also acting here. So liquid surface, without going into too much of detail, so what we understand here, if we look from energy angle also, see all it's a natural tendency for any object to minimize its energy state. So minimize its potential energy here. Since in case of a liquid here, energy is proportional to surface area. So liquid surface has a tendency to shrink, minimize the energy. How does it shrink? It tries to minimize the area, it tries to pull in. Exerts a pulling force on the boundary in the tangential direction. Wherever liquid is connected to any boundary, which could be imaginary boundary as a liquid surface also. So at any boundary, it exerts a pulling force similar to string. Only difference in case of string exerts a force at a point. It exerts force on a line where the surface ends here. And the force is tangential. And force is here, unlike a string here, this given for a particular liquid will have its own property, and it will have a surface tension. Surface tension is force per unit length. So it behaves like a stressed elastic membrane. So whenever you think of liquid surface, it's something like surface of an inflated balloon. If you take a kind of elastic surface, you stretch it from all directions, it becomes like that. Surface tension, there are two ways to understand here. One term is force, unbalanced force here. It behaves like a stress membrane. And surface tension we define in terms of force per unit length in Newton per meter. That becomes surface tension. And we can also define in terms of, we said, yes, all molecules near the surface have extra energy. So if I consider zero energy, this will have some energy here, some energy S here. So we define surface energy, energy per unit area. They have the same dimension, and actually it results to same part. It both refer to the same property. It leads to the same number. And so whatever force per unit length, energy per unit area, same dimension of force like water, it is something like 0.07 Newton per meter. We can also say it is 0.07 joules per square meter. Both are same thing. So that is, you can understand surface tension property in two ways. Surface tension in terms of force it exerts on its boundary, it tries to pull it in, and the force is per unit length and energy per unit area. Whenever it tends to shrink, minimize the energy. So these are basic property. We'll look at some application to understand that one. Let's imagine this is something like a bubble. Any liquid, it has formed a bubble here. And bubble, as we see bubble, mostly they are in the state of equilibrium. What happens if we cut open the bubble? We basically, it's just for purpose of analysis, I take the left half as one system and right half as system. This is one part and this is the right part. So what happens if we consider whole bubble together as a system, surface tension becomes internal force. It does not come into equation. So whenever we want to analyze surface tension, we need to take a part of the bubble. So we have taken one part. Let's take the left part here. See, this left part also is tending to shrink. If it is tending to shrink, it would exert a pulling force on the right part. The right part, there are two boundaries: the inner surface and the outer surface. So on this surface also, left part would have exerted a force like this, a pulling force. Similar way on these two surfaces, right part would exert a force like this. Force will act in which direction? Say this, if we take cut open, this is circle, and force acts tangential to the surface here. If I draw the tangent to the surface here, this will become a vertical circle here. All the forces will be in the horizontal direction. That's how the forces will act. And the force will act on the inner surface, and force will also act on the outer surface. I can show in the inner surface also. So if I analyze this bubble here, what other forces are acting on the bubble? This is a contact force between the left and right, and the contact force act all along the perimeter of the circle, on the outer circle as well as inner circle. In addition, there is a pressure force also acting. Outside pressure is say something P naught. And since all these forces are acting leftwards, the pressure acting inside the bubble has to be greater to compensate for the leftward force. So when you look at the pressure acting inside, this inside pressure has to be greater than pressure, external pressure. And then we arrive at, and so when we equate these two forces, what this equation comes to here. See this, I'm equating what we do here now. Sorry, we equate the forces in x direction. So surface tension, if I call T, surface tension is T per unit length. Force acting in the outer ring, if radius is r, it will be force into 2 pi r. And all of them are in the horizontal direction. This in the outer surface, force acting in the inner surface. Thus, the force towards right hand side positive force. What other force is acting? This force is P naught acting on the outer surface. And we have seen earlier also, if we take this force is always perpendicular to the surface. If we take its resultant of constant pressure force on any curved surface. If I am taking x component, it is equivalent to projection of area perpendicular to x direction. So its projection is pi r square. Force will be this plus P naught into pi r square. And this force also will be minus P naught plus delta P into pi r square. That's the equation we form based on, and this is something to help you understand two things. Is to help you also understand how does surface tension force act. Whenever you take a surface here, This is something for when we cut open the surface, this is where this boundary is. On the boundary, it acts along the length, it is per unit length, acts tangential to the surface. And from here, when we calculate, we find delta P is equal to 4T by R. And with sometimes surface tension, we also use convention as 4T by R or force by R is the excess pressure. So compared to water pressure is outside, inside pressure is greater to compensate. And you can also imagine something similar happens in a balloon. In the balloon also, which side, which direction they see inside the curved surface pressure will always be more. So if I take a elastic membrane, so whichever side I apply pressure, it will bulge out to opposite to that direction. Let's understand in terms of force on simple application. So there's a light wire AB, this wire AB of length 10 centimeter. It can slide freely on vertical frame, and there's a film of soap solution trapped between the frame. What you see in the blue color is a soap film. So soap film, just look at this. We are looking from one side. So there'll be two surfaces. One surface on our side, and one more surface behind it also. So it will form two surfaces. There'll be two air to liquid boundary, again liquid to air boundary. And what is the load W which can be suspended on this frame? This is frictionless from the wire to keep in the equilibrium. This has no weight. There's a weight W here. So when you look at what is the weight we can suspend here, it in the equilibrium. And surface tension is given in CGS units. So it doesn't matter. We'll deal with this. Everything will put in grams and all. So what is the weight it can suspend here? So here we'll consider this wire AB as my system. On wire AB, it has no weight. So what are the forces acting on the wire? This wire, it is connected to the load. So one downward force is acting weight. And this wire is in contact with the soap film surface here. Surface also will exert contact force. And what will happen, just this surface here, this is the boundary of the surface, and this surface is always trying to shrink. So if it is trying to shrink, what direction it will exert a force on the frame? On the left side, it will exert a force like this. Everywhere it will perpendicular to the boundary, inwards. Here also it will exert a force like this on this boundary. So all boundaries, it is exerting a force like this, is trying to contract. That's why it exerts a force like this. This is how the force is acting on the boundary of the surface. The first front surface, similar force acting on the back side. So if I look surface tension on two sides of L, if I look from the side, this is the side view. If I look from the side, this wire will have this kind of cross section. The front surface also is applying a force upward direction, and the film is upward. And how much this force will be? This force, if length is L, so this will be L into T in S into L. If I take surface tension S, front side and back side. So there are two tensile force acting, and this is W downwards. So this is the equation, and that's a weekend form. So not only solving this question, see that every part of surface tension property is understood here. A similar case could be like this. So this is kind of a picture. If you have a ring, rather than in previous case, a mass was suspended or rod was suspended here. So you just imagine that we have a circular ring and it is connected to two rods. And we insert this link. We keep it horizontal. And so this light wire ring of diameter gently lowered in liquid surface and then pulled up. And when you pull up, we notice here this liquid tends to stick to the surface of the ring here. And if you observe very carefully, it will tend to rise. And when it tends to rise here also all along the ring, the surface has become vertical. The surface becomes vertical. And if for some time, so if we apply force F here, it gets something like this. For a particular force F here, it is in a state of equilibrium. If I increase the further force up, the ring will come out. If I keep applying this force, it remains like this. If it remains like this, similar to previous case also, if we apply Newton's law of motion, if we consider this ring, the ring has no weight, but upward force F is acting, there must be equal to F force acting downward direction. And that F force is exerted by where would this surface exert a force? The surface is trying to shrink. So it will exert always a pulling force. It will exert a force on the ring in the downward direction. And there are two surfaces, inner surface and outer surface, both will exert a force like this. how much force will act? It will act on the perimeter, inner side and outer side. So total surface tension force will be twice the surface tension acting on the circumference, both inner and outer, and to become vertical as the ring is being pulled up. And hence we can equate the forces. Surface tension force per perimeter into 2 into surface tension. So force into length on which it is acting. And we don't have to component because since the film has become vertical, surface tension force also is vertical, equated to F. That's how to learn. And yes.
Sir, why do we multiply it by 2 in this case? Like, I mean, it's not mentioned, right?
Is there the inner surface and outer surface? Is there only one surface or two surfaces?
Okay, like we should always take it as two surfaces.
See, are there two surfaces or not?
Yes, sir. If the thickness is
There
not
has to be two
negligible, then
surfaces. There cannot be. Nobody need to mention. In this case, see, when we pull it up, there'll be some. See, when we have this liquid film, when we have liquid film, there's a liquid film here. This side also air. This side also air. If both sides are air, there are two surfaces. And when you lift it up, there's no reason this will get filled up. Yes, this also film will form. There's two layers. So let's another common example, and this simple experiment is useful for people to get an intuitive understanding of surface tension. So let's take a wire frame. So we have a wire frame, circular wire frame. It is dipped into soap solution. Soap solution is something as people enjoy playing with. It's easy to blow bubble with. So and it is taken out so that film of soap is formed. And we have a loop, a small thread, and the thread we measure this length of the thread. It is formed into a closed loop here. We place the thread here on, slowly drop this thread on the film. It stays there, gently put on the film, and then afterwards what you do, it has then, now this shape has not changed. Because what will happen whenever thread is there, if I take any part of the thread, there's a film on the left hand side, there's a film on the right hand side. Everywhere it will exert a force perpendicular to the thread and in horizontal direction. Since both same liquid on either side, the force on any part will be equal and opposite. So thread will not experience any net force. It will remain in any irregular shape you drop it in. But there's a film here, so we can put a needle through this central part. You put this central part, you run this needle through this. What will happen? The film will break. So only the film now remains between the thread and the ring. And what would this film do? This film will exert a force perpendicular to the length of the wire, and force is constant per unit length. Whenever force is constant per unit length, and this kind of force results in, it makes the ring into the thread in a circular shape. So any force which is perpendicular to thread and magnitude of force is constant and radially outwards, it turns into circular shape. So it can conduct experiment, it becomes like this. And we can understand this behavior. What is this film shown in blue color trying to do? It's trying to shrink now. It's trying to minimize its area by pulling on this boundary. It is trying to shrink from here to exerting a force on the ring like this, and it is exerting force on like this on the thread out. Whenever that force acts like this, it results in tension. So two ways to calculate here. One is, let me calculate this this is force is per unit length is F lambda. The force is F lambda here, and if I consider only the right part of the thread, I am considering the semicircular part. If I consider the semicircular part, everywhere the force per unit length is constant, but it is acting in the radial direction. Since in the radial direction, I cannot add up the magnitude. But if I have to take the summation of its component in x direction, it will be equal to projection of the length in the y direction. So net force acting on the thread due to surface tension will be equal to force per unit length into its projection is equal to 2r. That would be the force acting here, and this force will act up. And what is this force per unit length? Force per unit length is nothing but surface tension force. So one surface, upper surface, will apply a force on the, which I am considering semicircle. Semicircle, if I take this as x direction, if I add sum it up, resultant of x component, sum of x component here will be equal to s into 2r on the front surface, on the back surface also 2. So this is the resultant of surface tension force acting on the right part of the ring. Why I have taken only one part of the thread here, circular thread here? Because I want to find out surface tension force. So if I consider here, so now thread has two parts, right part and left part. Since I have taken only the right part of the thread, left part also would have exerted tension here. That's what you need to calculate here. It will exert a tension T here, and this had also tension T here. So this minus 2T, this is the, I have taken all the forces acting on half part of the thread is equal to 0. It gives you value of tension. What is the tension equal to? So tension anyway we had dealt with earlier also. So, we can also do using considering a small element of the thread. Other way of calculating would be you take a small element which subtend an angle of 2d delta theta. So tension will act like this. Tension will act at angle d theta d theta, and surface tension force will act in the radial direction. So here also we can do it. We can calculate here. In this case, we can take summation of force in y direction to be 0, and we can arrive at tension. So tension is force per unit length into R. That is something anywhere we come across, multiple places we come across tension here. Force per unit length. Here force per unit length is not S, it is 2S because it's acting on two sides. So if you take a small length dl here, it will act on the upper surface as on the lower surface. Hence, force per unit length is twice the surface tension into R. That's the tension here. So we can calculate this way also, or we can arrive at calculating this fashion as well. So we can easily put the numbers, so whatever numbers are given, any such case, and this tension we come across in multiple places, we should know how to easily calculate. Okay, this is little tricky question to understand here, and all of you notice. So if you have a ring here, and ring when we blow bubble, this is typically what we do. There's a ring of radius b here. We blow air. Air will have certain density. We blow air with certain velocity, and whatever air we blow, it will, see theoretically what will happen. It will strike the opposite surface of the bubble and come to a stop. So when it strikes it, it comes. That's what happens here. In the case of bubble, it will have a kind of collision with the surface, and air velocity will drop. So it will exert some force on the bubble. So when we blow the bubble, and all of you did noticed, and I'm sure all of you must have tried blowing bubble. So when we keep blowing with a constant velocity, it's difficult to maintain manually, but if we blow with some machine constant velocity, what we notice will it will keep growing, and when the bubble reaches a particular radius, then it gets detached from here and the bubble flies away. So what we want to calculate here, so what are the relevant parameters here? The relevant parameters is the radius of the ring, velocity is the air which is blown, and then somewhere density also will come, surface tension of the solution T, density. See, this force it will exert will depend on the density. The density, velocity, radius of the ring, and the radius of the bubble when it just separates from here. When it just separates. Until then, it is happy. It means stick to the ring here. So what is this radius when it separates from here? And of course, the surface tension of the material of the bubble. Okay, so how do you find the radius of bubble when it separates from the ring in terms of given parameters? So let's look at this question also. The force exerted by air on the bubble. So if I now I'm considering bubble as my system. So this air will exert a force dm by dt into v relative. We had done recently also. So the dm by dt is equal to rho av, mass flow rate into v. So this is the force a bubble is air is exerting on the bubble towards right. So there must be some other force must be acting towards left. This is exerted by air. And this bubble is only in contact with the ring. So there's a surface tension force. It is exerting a force on the ring in this direction, tangentially. And ring will exert a force tangentially like this. So if I take the horizontal component of surface tension force acting on the ring, that would be equal to force exerted by the air. Let's calculate. So basically, on what length the surface tension force will act? It will act on the length equal to perimeter of the ring, and it will act on the inner surface as well as outer surface. So we know the magnitude of force which is acting. If I add up magnitude, it will act for surface tension T, will act on length of 2 pi b inside and outside. But we need to take which component? We need to take the horizontal component. And everywhere we look at this, everywhere how this force will act. Let's see that one. Considering bubble as a system, equating forces in x direction, force by air is resisted by radial component of surface tension force acting along the ring boundary by inner and outer surface. It is acting on both surfaces here also. It's a bubble here. So if I look sideways, this is the ring here. If I look from the side, the ring looks like this, and this is R here, and this is B here. How would and surface tension field act perpendicular? So perpendicular, which direction surface tension will act like this? All along the ring, surface tension is so this if this angle is theta from the horizontal radial vector, this surface tension force will make an angle theta from the vertical. So I will take so whatever force acts here. So basically, what will be x component? X component will be if we get df into sine theta. Whatever force acts in a small element, df into sine theta. Sine theta is constant, so net force acting in x direction is equal to total force into sine theta. So equate. So basically, what we have done here. Okay, rho AV square. This term air force AV we have equated area in through which it is flowing through. This is equal to pi b square into v square. So force is equal to 2 pi b. Length it is acting. So force is equal to length on which is acting multiplied by surface tension. And since this is 2 is coming because it's acting on two sides. This is magnitude of force. If you multiply by sine theta, it becomes its axial component. And what is sine theta here? Sine theta is angle small. Sine theta is equal to theta. Theta is nothing but this side by r here. I'm equating sine theta as theta here. Theta is equal to b by r. I substitute in place of sine theta is equal to theta is equal to b by r. I get my answer. And this question, yes,
So why are we taking net force 0?
bubble is in equilibrium. Just before it leaves, it is in the state of equilibrium.
So, but then it is expanding, right? The center of mass is moving.
See, I am not taking center mass. I am taking this if okay, the bubble. Okay, but this if at all you need to look at. Are we including air inside? I'm not taking air inside. The air effect of the air also is taken as a contact force. We are just taking the bubble here. If we taken the bubble mass or weight, does it make a difference here? No, it doesn't make a difference. Okay. So this is something I think you can keep an eye. So air is not part of the system. What is taken here is a bubble film only. And contact force exerted also air by air also has been taken into account here. And just before it breaks off, it is in a state of equilibrium. And that's how we can solve that. And of course, if somebody may question this one, you can analyze, but there's no other way to solve this question. And this question has come 3-4 times in the exam in different forms. Okay. And we have similar way. Okay, we'll come to one. I think I have given in worksheet a similar question, which has come very similar to this. Let's try and solve that question as well. Okay. So if at all you have to look at, okay, if somebody may think if what is the center of mass which is in motion, if I have to look at, I have to take the center mass of bubble mass which is in motion, and bubble mass here is negligible. So another way, even if you think the center mass here, I am taking the bubble only as a system. So practically it's massless here, so net force has to be zero at all instances. There's no question of motion of center mass. So next question, large number, but it was a good observation anyway, Ella. A large number of liquid drops, each of radius r, coalesce to form a single drop of radius r. And this you could have seen many times. The drop also window panes, you can notice some drops come and they coalesce together. So energy released in the process is converted into kinetic energy of big drops so formed. What is the speed of big drop? And some of you feel that question looks funny, but these are all questions which actually come in the examination. And actual examination, yeah, you may always find flaw with the question. This may happen, that may not happen. How would you acquire speed and all? But this also is the actual question. And what we need to look at, we need to look at what is the information given and what best way we can solve the question. If any we have to make certain assumption, make assumption and solve the question. Every time we need to keep in mind. So large number drop. So now and why they from coalesce. So coalesce, okay. So what are things happening here? Two things have to happen here when they coalesce. A large number of drops. So let's say how many number of drops? A number of drops, each of radius r small r. So volume of liquid remain constant. The liquid is incompressible. Since the mass remains constant, the volume also remains constant as the density is constant, which is because of incompressible nature of the liquid. So it forms the radius r. So the relationship between radius of initial small drop and the big drop it forms this equation. So this gives you a relationship between radius and number of drops which have coalesced here. Second thing, when we talk of energy released, we basically come from whatever work done. Work done by non-conservative force, if it is positive, is equal to energy supplied. If work done is positive, what does it mean? It means energy is being added, and energy is being added here. If this entire energy goes in form of potential energy, it leads to this something we write PF minus PI. And if energy is positive, this whole term final potential is greater, initial potential energy is smaller. But when we say when energy is released, we are talking about energy release means energy supplied is negative. So there's a loss of energy. So when we talk about loss of energy, we write initial potential energy first and final later. So energy released because why it is released, initial energy was greater, final energy has become less. So initial surface energy and minus surface energy. Energy has released only because of change in surface energy. Nothing else is changing here. Somebody will say the wrong yes, okay. So what is energy released here? So what is initial surface energy? Initial surface energy is surface area into surface tension. Surface tension energy per unit area, I multiply by for surface area of the drop. And since the n drops, add it up, multiply by n. So n 4 pi r square into t is initial surface energy. This is the final surface energy. So this energy released, and this energy is converted into kinetic energy. So what we do, this entire thing we equate to kinetic energy. Kinetic energy equal to 1 by 2 mv square. 1 by 2 mass also a big drop is formed is written in form of density and volume into v square. And that's the equation we form here. And we need to find here velocity. So after getting this one, the final answer. So again, depending on whatever options are given, you can substitute in place of nr, and if I write as nr cube, I could have written nr cube divided by r, and then in nr cube, in place of nr cube, I can write r cube. So that was how the answer was. We use this relationship, substitute here, and get our answer. Okay, this is a fairly simple question to understand about air bubble. Air bubble is one special thing we need to keep in mind. So there's air bubble of radius r at a depth h. Okay. Again, see, every time the question may not be mentioned. Okay, so this depth, this r at a depth h, and whenever I say depth h, depth h is meaningful only when we different parts of the bubble may have different depth, but we consider this to be too small compared to h here, then only we can mention a particular depth for the entire bubble. This automatically, see, the wording itself implying this radius r is much smaller than h. Otherwise, the bubble could not have a unique depth here. But as some instance, so this is the depth here. It is inside water at depth h. Is the atmospheric pressure. So d is the density of the water, and t is the surface tension of the water. What is the pressure inside the bubble? So in case of bubble, we have seen earlier also, there's an excess pressure. In case of bubble, excess pressure is bubble in air. If bubble is in air and bubble in water, there's a difference between the two. If bubble is in air, see what would happen in that case if this is the bubble surface, the film, there's air and there's a liquid surface, and again there's air. So there are two air liquid boundaries. One is outer surface, one is the inner surface. When bubble is in water itself, what has happened? The outer surface which was in contact with air, now outer surface of the liquid is in contact with the liquid itself. Now it is something like this. If it is a bubble here, there's a liquid here, and there's air here, and the surface also liquid. So air to liquid boundary is only one. So since here in this case there are two surfaces, as the excess pressure becomes 4T by R or 4S by R, whichever notation we use, it becomes equal to 2T by R. Whenever bubble forms inside the liquid, surface excess pressure is 2T by R. And let's try understand what is excess pressure mean. So excess pressure mean here, if I call this point as O, which is inside the bubble, and point P is outside the bubble. So this point has some pressure, this point has some pressure. pressure at O will be pressure O minus pressure at P is excess pressure. Which side is excess pressure? The pressure is more whichever side the surface is curving, whichever side the center lies, toward the center the pressure is greater. Also this equation, this excess pressure, and we can easily find here pressure outside the air bubble. So pressure at P is equal to atmospheric pressure plus dgh. Density is given not in rho, dgh, that's the pressure P. So pressure in the bubble, it will be, if we add to this term 2T by R, that becomes there's only one surface. Hence it becomes equal to this term plus 2T by R. That's the pressure inside the bubble, absolute term. This is absolute pressure, and this pressure can be used for any gas law, any ideal gas equation. Okay, this also, if you have a container, if container has a small hole at the bottom, and if you take a liquid here and try to push this container into the liquid, I'm talking about not a big hole, it's a very small hole of order of maybe millimeter or so. As we push, what we notice here, if we push up to certain depth here, we have pushed it inside the liquid to certain depth h here, still we find the water has not started coming in. Water has not started coming in, and if we observe using an instrument which you can make a close observation, will form a spherical surface will form here. The spherical surface will keep forming here at the boundary. So this surface becomes like this side is liquid, this side is air. So as we keep pushing down, the radius of the surface which keeps forming here will keep on decreasing here. So this what happens when an empty vessel with a small hole at bottom is immersed in water or any liquid up to a depth h. So what it says, if we insert for a depth less than h, the water will not seep in. If the depth is h, it is on the verge of coming in. With a slight increase in depth, the water starts seeping into this, getting into the vessel. In surface tension, find the expression for radius of hole in terms of rho h and how is radius of hole related to surface tension and h. And if you understand figure here, you can understand here as we keep increasing, the radius will keep on changing. So what has to happen here? In this case, it will form something like a part of a bubble. It will not form a full bubble. It will be part of a spherical surface. And as it forms a spherical surface, here the pressure is atmospheric. And here, just below the surface, pressure will be P naught plus 2S by R here. What is R here? R is the radius of the spherical surface which forms. And this has to be equal to, this is the pressure at this point. And this pressure I have calculated based on the surface tension property, based on the curved nature of the surface here. But if I calculate same point at similar depth, if I calculate from here also using the hydrostatics principle, the pressure at this point is P naught plus density is given rho g. These two have to be equal at all instances until the surface is broken. So as we dip it into up to a depth h, if water is not seeped in, this has to be equation. It means surface is formed which is of a shape of a sphere. So P naught plus 2S by R has to be this pressure I have calculated based on what? Just above the surface here and just below the surface. There's a difference in pressure. I have used that property here. And we calculated same depth. I have calculated pressure from here also. And since it is connected liquid, the pressures have to be equal. So I use that property, and this is equal to P naught plus rho g h. And as we notice here, as h increases, these terms are equal. Other terms cannot change. R will keep on changing. So radius of spherical shape which forms here, it will keep reducing as caps increasing, but it cannot keep reducing. Minimum value of this radius of spherical surface which form has to be equal to radius of the hole. So what is the boundary? As the pressure is lower, pressure on one side of the surface will increase, and it will require a shape of a part of a spherical shell. And as the radius will keep on decreasing as delta p keep increases until the radius becomes radius of the hole. and that's the time it will just break into. So this equation here. So what is H maximum? When H is maximum, R is minimum. What is the equation I would have written for H maximum, R to be minimum? The equation would have written here: limiting state, radius of the surface is equal to radius of the hole. I substitute small r, I get the maximum H here. Rho GH is equal to 2T by R. That's the equation. Again, you notice here only one surface, only one boundary, not 4T by R. One side liquid and air. There are no two boundaries. This is a relatively simpler question. So what you notice here, so there's a small soap bubble. You would have seen, if you are too smart, you can do that. You can blow bubble inside a bubble. Ordinary people find it difficult to blow bubble. People who are smart can do that. So soap bubble of radius 4 centimeters trapped inside another bubble of radius 6 centimeters. So two bubbles here. What we see in circle here in 2 dimension. Actually, in 3 dimension, there are two bubbles. So soap bubbles. Outer one has a radius of whatever 6 centimeter, and inner one has a radius of 4 centimeter without any contact. P2 is the pressure inside the inner bubble. P2 is the pressure inside the inner bubble. Everywhere pressure is same. Why the pressure is same here? Density is small. So pressure at this point compared to this point, the pressure should have been higher by rho GH, but rho GH is negligible. So we assume in air on small heights, pressure to be uniform all across this volume. So okay, and outside pressure is exposed to P naught. P naught is the pressure outside the outer bubble. So what is asking here? What is the radius of another bubble? Which has same pressure. Now this is pressure P2 here. If I have another bubble and this bubble also is blown in the same atmosphere, this bubble also has a radius P2. What is the radius this bubble has to have? Will it have radius of 4 centimeter? No, actually it will not have 4 centimeter. It will have some different radius. So what is the bubble radius should be so that it has same pressure as P2 pressure inside the smaller bubble? It's also fairly simple question. Excess pressure is equal to pressure inside minus pressure outside. That's excess pressure. So if I calculate the pressure here P1, P1 is the pressure in the entire region between outer bubble and inner bubble. So P1 minus P0 is 40 divided by radius of outer bubble. The radius of the surface here. See, when we cross a surface here, the pressure changes. And the change in pressure depends on the radius of the surface. And this is what we are using here. It need not be in spherical. So whenever there's a for surface curved like this, it is like this. So for 40 by R here. And this is bubble. So two surfaces here. This gives you P1. Similar way, this bubble, excess pressure is P2 minus P1. This here pressure is P1. This is P2. P2 minus P1 is excess pressure, which is equal to 40 by radius of this bubble. So from this, I can find out P2 minus P0 is this value. And if I have another bubble which has radius P2 and outside pressure is P2, this also should have excess pressure equal to P2 minus P0, and P2 minus P0 that has to be 40 by R. If I substitute, I get the value of R here. Okay, this is something I think question which is a little tricky. And you would have seen if there are two glass plates, and I will focus on the left part. So what you see, this is we are looking at side view here. So we keep two glass plates parallel to each other, and both are in the horizontal plane. So we are looking in this horizontal plane. This is the top plate, and this is the bottom plate. And there's some amount what you see in the blue color. This is some liquid which is trapped between the two plates here. This top plate, bottom plate, and whole thing is kept on horizontal surface. When we leave it like this, no external force is acting. And again, if you observe closely, you just look at the left part, right part I have not drawn, and I find this surface will be slightly bulging out here. And if I continue the surface here, it will be part of a spherical shell of some radius r here. Okay, it will bulge out. The question comes when I'm saying bulging out, why should it bulge out? Let's like to understand first this part. So I'll do the 2-3 steps in this question to understand what happens to liquid which is trapped between two plates. So curvature of the surface, so when it is related, so when the curvature of surface and pressure in the liquid are related. So as the curvature, it curves like this, if the radius is r, outside pressure is P0, it means entire liquid, not entire liquid here. The moment we cross here, the pressure becomes more, the pressure inside becomes pressure on the inner side of the surface becomes P naught plus 2T by R. So it will take a surface of, if the plate is kept like this, entire liquid here is at a pressure P naught plus 2T by R. So if I look at this plate here, if I look at the plate as a system, there's an excess pressure inside. So if I look plate as a system, what are the forces acting on the plate? Its weight is acting downwards. Something, and if you look at the part where liquid is not there, if liquid is not there, pressure is acting P naught downwards, pressure acting P naught upwards. This will not exert any net force. Only where liquid is there, one side air, other side liquid. Air is exerting force of P naught downwards. Liquid is exerting a force P naught plus 2 by R upwards. I can remove P naught and P naught. It is equivalent to whenever this excess pressure, it will exert net force will be equal to excess pressure in pushing direction. That's a net force exerted by the liquid which is in contact. So in a state of equilibrium, what is the radius here? So if the liquid is spread over an area A, what is the liquid? We can see from the top or what area the liquid is spread here. Weight will be equal to delta P into area of liquid spread. And then I can find out if I take the liquid, it can have any irregular shape also, doesn't matter, but everywhere inside the liquid, the pressure will be same. And I can equate W will be equal to delta P is equal to 2P by R into area. So you understand from here. So this is something, the radius will depend on how heavy the plate is and what is the area of the liquid. Okay. So this is something I think one part we need to understand. This question I have taken up so that we understand behavior of uh, surface tension and behavior of curved surface. Again, to repeat the point, whenever there's a curved surface here, this is outer side, this is inner side. Inner side will have excess pressure. Moment you cross the curved surface here, pressure will change. This side of the boundary, different pressure, this point of boundary, different pressure. And this pressure will be higher by 2T by R, R being the curvature of the surface. Okay, hence must have positive extra pressure. Now what we do here, if we start applying an upward force, we try to pull the force plate up. That's why we are trying to lift the plate up. We are applying a force which is acts more than weight here. So now if I consider the equilibrium of the top plate, there are two forces acting. Weight is acting and upward force what he applied is greater than weight. It means net force has become upward. So if the plate has to remain in equilibrium, the net force exerted with the liquid has to be in the downward direction. How does it become downward direction? It cannot exert a pulling force. Let's understand what will happen here. The outer part pressure will cancel out. Just look at the liquid part what will happen. So liquid part what will happen if this pressure outside in the plate, upper surface of the plate will have pressure P naught, and lower surface will have a pressure is equal to P naught minus delta P. So what will happen? Why it is just T delta P? So if I cancel out P naught, it will behave as if there is a pulling force, suction pressure. You know, suction, sometimes you feel something is pulling it in. So it will have lower pressure. Whenever pressure is lower than atmospheric, net pressure becomes equal to suction pressure. This pressure has to be lower than atmospheric delta P. And if it has to be lower, just see that one now. So this is a region with the curves, this surface here, it will take a curved shape of radius like this. Their pressure is atmospheric. As I cross here, I am going from inside the liquid surface to inside the curved surface to outside the curved surface. So pressure will drop by delta P here. So pressure inside the liquid, since it is not convex surface, when it is concave surface like this, the pressure inside the liquid is lower. Is lower by how? To understand, this was a convex, it was bulging out, pressure was higher because center was inside the liquid. Now the center is curving outwards. This is concave shape looking from inside the liquid. The pressure will be lesser than atmospheric pressure. And so what is the net force acting in this case? If I again draw the summation of force is 0, I have applied a force F, and which is not adequate to lift the plate. So I'll write force minus W minus delta P is equal to 0. So net force F minus W will be equal to delta P, and delta P will be equal to 2T by R1 being the radius. What will happen as I keep increasing the force here? If the force is increasing, weight remaining same, this part also has to increase. It can only increase by R1 reducing. The radius of curvature keep getting smaller and smaller as we increase the force. What is the condition? What is the maximum? What is the force I need to apply to separate the plate, lift it up? So it will keep getting smaller, but if the distance between plate is equal to T, the minimum radius has to be equal to T by 2. It cannot become smaller than T by 2. So what is the condition for plate to be pulled apart? If I ignore this force to be much larger than weight, I can write the equation. The net force, what we need to apply, has to be equal to 2T by R3 here. What will be R3? R3 will be equal to separation between plates divided by 2. That is the force I need to supply. And you notice here, smaller the thickness of water layer is, more difficult it is to pull it apart. It behaves as if there is suction here, suction pressure kind of act. And so you, I hope you get some sense of what does suction pressure mean. Suction pressure mean the pressure here is lower than atmospheric pressure. It tends to pull the surface in. Actually, it is still exerting pushing force. The contact force is only pushing force. But since it is lower than force acting on the other surface, it appears like a suction pressure. It's a gauge pressure. Gauge pressure here is negative here. Okay, so this is when it is about to get pulled off. This is how the surface will change. If I draw this curvature here, if I complete the sphere here, this is how the surface will look like when it is about to be pulled apart. Divide. So that's what happens when the liquid gets trapped between two parallel plates, and we try to pull it apart vertically. In limiting state, radius surface is minimum. That is equal to half the gap between plates. And which is the area? Area is the surface over which the liquid is spread. Okay, some more questions which have come in mains. And a soap bubble blown by mechanical pump at the mouth of tube increases in volume. Soap bubble is very popular in surface tension. The soap bubble is based on surface tension property. So what are we doing? We are this mechanical pump is blowing in such a way that volume increases at a constant rate. Volume rate of change, it is volume is a direct linear function of time. So whenever you say something like this, when you say volume increases at a constant rate, volume is directly proportional to time. Volume is directly proportional to time. What is given here? Now the question asked here, which of the following graph correctly depicts time dependence of pressure inside the bubble? So which of the graph is the time dependence pressure and the time pressure inside the bubble? This is pressure. So whenever graph is there, what we need to do, we need to find an equation which is between pressure and time. So we need equation between pressure and time. What is given? Volume is varying directly with time. So this fairly direct question. What is pressure inside the bubble? Pressure inside the bubble is P naught into 4T by R here. R being the radius. Radius is changing because volume is changing linearly with time. So since volume is related to time and radius also is related to volume, I can write R in terms of time here. Moment you write in terms of R in terms of time, I get equation between pressure and time. The moment I get equation, I can know which of the graph is correct. So that is what volume is directly proportional. So volume is 4 by 3 pi r cube is equal to proportional to time some 80, which basically means R is proportional to. Here, all these cases, we just need proportionality. R is proportional to P raised to power 1 by 3. In case of R, I substitute P is equal to P naught. Get some constant divided with T raised to power 1 by 3. So if I want to get a linear equation, if I take this as Y, what has to be my x to get a linear equation? X has to be equal to 1 by t raised to power 1 by 2. That has to be the equation. Then only if I on x-axis, I need to take t raised to power 1 by 3. But the way the exam, the question had come, this question in the mains also had gone as a bonus question. Why it was a bonus question? It was given 1 by t to power 3. Actually, this initially they gave us a correct answer. It should not be 1 by t raised to power 1 by 3. It should have been t raised to power 1 by 3. Then only the answer would have been correct question. So this is again graph. So every time we come across a graph question, first thing should come out to mind. I need to find an equation between pressure inside the bubble and the time. Pressure inside the bubble, I know in terms of radius, And since volume is related to time, radius also I can relate to time, get an equation. And since it is a straight line equation, unless I use this quantity, if it has this quantity has to be x 1 by t raised to power 1 by 3, then only I get a straight line equation or for a straight line. So very simple. And we have done a similar question, a straight line question, sometime even in case of rotation motion also, rod hanging kind of thing. So this graphs are very popular question. In every paper you get a couple of question on graph. So if you practice, you find these are very easy question to answer. Right. This also in the question if S and B are change in surface area and volume. Okay, so I'll do one thing. I'll just stop here, take a small break, and I'll continue after 10 minutes. Just take question.